The RS system is used to describe the configuration of a chirality center. Down here we have a pair of enantiomers. On the left we have one compound. On the right we have its mirror image. We're going to assign an R or S to each of our enantiomers. So let's start with step 1. In step 1, we prioritize the 4 groups attached to our chiral center. And we do that according to atomic number. Let's start with the enantiomer on the left. We know that this carbon is our chiral center, and we have 4 different things attached to this carbon. We go over here to the right to a very shortened version of our periodic table, and we can see that bromine has the highest atomic number out of these 4 atoms. So bromine gets highest priority. We're going to give the bromine a number 1. Chlorine has the next highest atomic number at 17, so chlorine gets second highest priority. Fluorine has the next highest with a 9, so fluorine gets a 3. And finally, hydrogen is the lowest priority group with the lowest atomic number of 1, so hydrogen gets a 4. So step 1 is done. Step 2, orient the groups so that the lowest priority group is projecting or pointing away from you. Our lowest priority group is hydrogen, and it's already going away from us. The hydrogen is on a dash here. So step 2 is pretty much done. Step 3, determine if the sequence 1, 2, 3 is clockwise or counterclockwise. So we're going to ignore our hydrogen here, so I'll just kind of rub it out here, and look at what's happening with 1, 2, and 3. So 1, 2, and 3 are going around in this direction. That is clockwise. Therefore, this is the R enantiomer. So I'm going to write R bromochlorofluoromethane. Let's do the same thing for its mirror image. So this compound on the right, we know that this carbon is our chiral center. We already know how to assign priority. Bromine gets a number 1, chlorine gets a number 2, fluorine gets a number 3, and hydrogen gets a number 4. So step 1 is done. Step 2, point the lowest priority group away from you. Well, that's already happening here, so step 2 is done. Step 3, determine if the sequence 1, 2, 3 is clockwise or counterclockwise. So let's ignore this group going away from us, the lowest priority group. And let's go around 1, 2, and 3. So going around in a circle, 1, 2, and 3 in this direction. We know that is counterclockwise. So this must be the S enantiomer. So this would be S bromochlorofluoromethane. So step 3 is done. So that's how you assign a configuration to a chiral center. Here we have another pair of enantiomers. So this alcohol on the left and its mirror image on the right. Let's start with the one on the left. We know from earlier videos that this is the chiral center, and our goal is to assign a configuration to this chiral center. Let's go ahead and redraw the molecule. So that carbon is our chiral center. Attached to that carbon is our OH, so I'll draw the OH on a wedge. We know that hydrogen is there going away from us, so that's a dash. So even though it's not drawn in, we already know it's there. To the right we have a methyl group, so a CH3, so let's draw in a CH3. And then finally to the left we have an ethyl group, so that would be a CH2 and then a CH3. Alright, let's go back to our chiral center. So here is our carbon, that's our chiral center. Let's look at the atoms that are directly bonded to this carbon. So there's an oxygen directly bonded to the carbon, there's a hydrogen, and then we have 2 carbons. So let's assign priorities. If we look over here at our very shortened version of the periodic table, we know that oxygen has the highest atomic number out of those atoms. So oxygen gets highest priority. The OH group gets the highest priority. So this gets a number 1. Hydrogen has the lowest atomic number. So the hydrogen is the lowest priority group. So we say that's group number 4. Finally, we have 2 carbons, and 2 carbons would of course be a tie. Carbon has atomic number of 6. So we have to find a way to break the tie. So the way to do a tiebreaker is to look at the atoms that are directly bonded to those carbons. So we'll start with the carbon on the right. The carbon on the right is directly bonded to 3 hydrogens. 1, 2, 3. So let's go ahead and write that out. So hydrogen, hydrogen, hydrogen. The carbon over here is directly bonded to a carbon, a hydrogen, and a hydrogen. And we're going to put those atoms in order of decreasing atomic number. So this carbon has a higher atomic number than these hydrogens, so we write carbon, hydrogen, hydrogen. Next, we compare these lists. So on the left, we have carbon, hydrogen, hydrogen. On the right, we have hydrogen, hydrogen, hydrogen. And we look for the first point of difference. Well, that's carbon versus this hydrogen here. Carbon has a higher atomic number than this hydrogen, so the carbon wins. So this group gets higher priority. So the ethyl group has a higher priority than the methyl group. So the ethyl group must be the second highest priority. So this gets a number 2, and the methyl group must get a number 3. So now we've assigned priority to all of our groups. Let's go down here and let's write it in. The OH got highest priority, so that gets a number 1. The ethyl group got second highest priority, so that gets a number 2. The methyl group got third highest priority, so that's a number 3. And the hydrogen, our lowest priority group, is pointing away from us, so that takes care of step 2. Step 3 is to see what the sequence is doing. So if we go around a circle, 1, 2, 3, we're going around this way, right? We're going around clockwise. And we know if we're going around clockwise, that must be the R enantiomer. So this is R2-butanol. If that's R2-butanol, the mirror image must be S2-butanol. So let's go ahead and let's double check and make sure that's true. So this is our chiral center. This is our chiral center. We know the OH is highest priority, so that gets a number 1. Let me go ahead and change colors for this. So this one gets a number 1. We know that our ethyl group gets a number 2. We know our methyl group gets a number 3. And we also know there's a hydrogen going away from us in space. So our lowest priority group is projecting away. So all we have to do now is look at what's happening with 1, 2, and 3. And 1, 2, and 3 are going around this way. And that, of course, is counterclockwise. And counterclockwise is S. So this is S2-butanol. We just saw that this is S2-butanol. But what if you were given the dot structure on the right and asked to assign a configuration to the chiral center? So here is the chiral center. And if the OH this time is going away from us, that means that the hydrogen is coming out at us in space. So we've already seen how to assign priority. The OH gets a number 1, the ethyl gets a number 2, and the methyl gets a number 3. And the hydrogen gets a number 4. When you go to step 2 says to orient the group so the lowest priority group is projecting away from you. But that's not what we have here. Here we have our lowest priority group coming out at us in space because this is a wedge. So one thing you could do would be to take this compound and in your head mentally rotate it so the hydrogen is pointing away from you in space. And when you do that, you'll see that it's the same as the one on the left. So this is just 2 different ways to represent the same enantiomer. So in the video on drawing enantiomers, I actually showed you the video where I rotated this compound to prove that these 2 drawings represent the same compound. So now your hydrogen is going away from you in space, and that's how we got S, because this was a number 1, this was a number 2, and this was a number 3. So we went around this way, and we saw that is counterclockwise, and so we got S. But what if you didn't want to rotate the molecule in your head? Sometimes it's pretty difficult to do. For this one, it's not too bad, but it can get a little bit tricky. So there is a trick that you can use. There is a trick that you can do. And you can just start with the drawing on the right. You can go ahead and number your groups in terms of priority. And then you can go ahead and just ignore the hydrogen for the time being. Even though the hydrogen is coming out at us in space here, if you ignore it, and look at 1, 2, 3. So 1, 2, 3 is going around this way. And that would be clockwise. And we know that clockwise is R. So I'm going to write it looks R here. It looks R. But since the hydrogen is coming out at us in space, we can take the opposite of how it looks. So if it looks R and the hydrogen is coming out in space, you know it's actually the S enantiomer. So that's a little trick that you can do. Instead of rotating the molecule in your head, you can just assign your priorities, come up with R or S, and then take the opposite.